Hello, I am Eren ÖZPOLAT. In this video, we will present our graduation project that is machine learning-based modulation recognition for wireless communication systems.
Hello, and I'm Nihat GEZGİN. The main goal of this project is to identify modulation types using deep learning under realistic wireless channel conditions while working with the SDR hardware.
In classical modulation recognition, the receiver relies on likelihood-based or handcrafted feature-based methods, where decision boundaries are defined analytically. These approaches assume accurate knowledge of channel conditions such as noise level, synchronization, and fading. However, in real-world scenarios, these assumptions often break down, leading to degraded performance. To address this limitation, we adopt a machine learning-based approach that directly learns discriminative features from raw IQ samples. This data-driven method allows the system to remain robust under realistic channel impairments without relying on explicit decision boundaries. Our system is based on a one-dimensional ResNet convolutional neural network with approximately 9.3 million parameters. The model operates directly on raw IQ data, where each input consists of 1024 complex samples represented as two channels for the in-phase and quadrature components. The residual architecture allows the network to be relatively deep while maintaining stable and efficient training. During development, several neural network architectures were evaluated, and the ResNet-based model achieved the best performance. The model was trained on the RadioML dataset, and the latest stages of the project focus on setting up the SDR, backend, and the frontend to evaluate this pre-trained model under realistic channel conditions rather than just retraining it. As shown in the accuracy versus SNR results, the ResNet-based model clearly outperforms the standard CNN, especially at moderate and high SNR levels. At this stage, the training phase is complete and the focus shifts entirely to testing. Test signals are synthetically generated by us and made realistic by introducing real-world channel and hardware impairments such as additive white Gaussian noise at different SNR levels, fading, Doppler effects, carrier frequency offsets due to oscillator mismatches, sampling rate offset between transmitter and receiver, phase noise, and related effects. These signals are then transmitted and received through the SDR transmitter and receiver chains. The received IQ samples are processed in the backend, classified by the pre-trained model, and visualized on the front end. This end-to-end setup allows us to evaluate the robustness of the model under realistic RF conditions rather than ideal simulations.
The system pipeline starts from a user request and proceeds through an end-to-end processing flow. IQ samples are first transmitted and received through the SDR transmitter and receiver chain, after which they are forwarded to the backend. In the backend, the incoming IQ stream is pre-processed and formatted to match the input requirements of the pre-trained ResNet model. The processed data is then passed to the model, which performs modulation classification. Finally, the predicted modulation results are sent to the front-end and visualized live, enabling continuous monitoring of the system output. The front-end interface allows the user to control key SDR parameters and to randomly select test signals from the dataset. As inference is performed, the predicted modulation type is displayed in real time. In addition, the normalized IQ samples are visualized alongside the classification results. This enables continuous monitoring of the received signal. In this example, a test signal with an 8 amplitude shift keying modulation is transmitted and received through the SDR. The pre-trained model correctly identifies the signal as 8 ASCII with high confidence. The class probability distribution shows a strong dominance of the correct modulation class, while the remaining classes stay close to zero. This indicates reliable and stable classification performance under realistic channel and hardware impairments. We presented a deep learning-based modulation recognition system evaluated using realistic simulated channel and hardware impairments. The end-to-end pipeline, together with front-end visualization, demonstrates robust and reliable classification performance. We would also like to thank Dr. Raşit TUTGUN
And Dr. Emre AKTAŞ for their guidance and support throughout this project.